Now let's investigate the chain rule with our trig functions to see if we can come up with some more rules that make our life easier so that we don't have to do the long version of the chain rule each time, we can take a shortcut. Now this question's a lot simpler than the one below. This one just has a 3 out the front of the x, so differentiating the part in here is quite simple. It's in the form ax plus b, whereas this one is a much more complicated function. We're looking for a rule where we can put some f of x in here and see what to do with it. So the slow version of the chain rule says take the complicated part and call it u, and we can differentiate u with respect to x. So du dx here would be just differentiating this, we get 3. Then we can rewrite our function with u in it. If y is now the sine of u, then we can differentiate y with respect to u and say we get the cos of u. Just like differentiating sine x gives us cos x, differentiating sine u will give us cos u. Now to get dy dx, we can do dy du times du dx, and that gives us 3 multiplied by the cos of u. So we'll put the 3 out the front and put cos, but instead of putting u, let's write down what u actually is. It's that complicated part. All right, what's happened? Well, this looks quite familiar, doesn't it? The 3, which is the differentiation of the part in the brackets, has come out the front. It's quite reminiscent of when we differentiate something like this. We found that y dash, we bring the 3 out the front, and then we rewrite what we were given. Similar, we're rewriting the part in the brackets, the 3 is coming out the front, but we're changing from sine to cos, because when we differentiate the sine of something, we get the cos. So this rule makes a lot of sense with things that we already know. All right, let's apply the slow method to this one as well. Let's let u equal 2x cubed minus 7x. So then du dx will be 6x squared minus 7. And now we've rewritten the function y equals the sine of u. We can see that dy du would be the cos of u. Therefore, dy dx is dy du times du dx. So we have this 6x squared minus 7. We'll put that out the front in brackets, multiplied by the cos of. Now we don't want to write u because u wasn't in our question. We just made that up and used it. We want to write what u actually is. 2x cubed minus 7x. And there we have it. Does it fit the same rule as the one above? Yeah, it does. Differentiate what's in the brackets, toss that out the front, change your sine to cos, because sine differentiates to cos, and then rewrite the brackety part. So now we've got 3 more formulas that we can write in our book, put a big friendly box around them, and let's learn these. They are also on your reference sheet. Now you'll notice that the reference sheet doesn't have the simple version of these formulas. It doesn't have sine of x. If we differentiate, it gives us cos of x. But as we know, if we've got the more difficult formula, we can do the difficult questions with it. We can also use the more difficult formula for the simple questions. Because obviously, if you're looking at differentiating the sine of x, x is a very simple function. Your f dash x that will be out the front is just 1. So if you forget the simple rules, the complex ones will still help you. So 3 examples here so that we can practice using our formulas. The first thing to know is that if you have a constant out the front of all of this, it comes along for the ride as well. We've learnt that with all our other differentiating and our integrating, in fact. So this question looks trickier having the 4 there, but that 4 is just literally going to come along. So here we're differentiating some function. This is our function of x. So what we need out the front is we need our 4, and we need to differentiate what's in the brackets here to find our f dash x. And what we get is 3. So the 3 comes out, multiplies by the 4. I can do that in my head so that I can write everything down in one go. I differentiate sine to get cos. And then I need to just rewrite that function that's in brackets. No matter how complicated it is, I can just write it down again. And that's it. Now this one looks simpler than it is. It'd be best to rewrite it first, so that we're really clear what it is that we're actually differentiating. We are differentiating the tan of x all squared. So here we basically need to use the chain rule on this. where we bring the 2 down the front, we differentiate what's in the brackets and bring that out the front, and then we rewrite this but drop the power down by 1. Now this is a different version of the chain rule from what we were doing here. Our chain rule was to say, hey, we're doing the sine or the cos or the tan of some function. Let's let that be u and work out what to do with it. This is a good old-fashioned version of the chain rule that we would use just when we're differentiating something like this, say, bring the power out the front, differentiate what's in the brackets, bring that out the front too, then rewrite everything in the brackets and drop the original power down by 1. That's what we need to do with this one. So rewriting it like this to me looks a little bit friendlier. I'm going to bring the 2 out the front. I'm going to differentiate what's in the brackets and bring that out the front. And I know that the tan of x differentiates to give sec squared x. And then I need to rewrite what's in the brackets but drop the power down by 1. So it'll just be tan x to the power of 1. That's just tan x. So I can just write it like that. And I probably don't even really need the brackets. I've got 2 multiplied by this, multiplied by that. You can put a little dot in between if you want to, but it's not essential. You could put brackets as well. Now this one's a bit of a trick question. If that just said cos x, I would say minus sine x. But it's got a little degrees symbol there, and that's quite tricky. Now, we said that we can only differentiate and have the answer mean anything whatsoever if we're measuring in radians. And that's because that makes the scale of our graphs so that the y-axis and the x-axis are actually in the same proportions, so that the gradient means something. If we're working in degrees, we can't use any of these rules. So I have to start by switching x degrees to radians. Now, how would you know that any of these other questions were in radians? Well, they didn't have units on them. See how this one's got degrees written there? And remember that radians don't have units. The reason they don't have units is because by definition, remember when we first learnt what a radian was, we said if we take some length of an arc and we divide it by the radius, that's what radians are. Now, lengths are always measured with units, aren't they? If we measured the length of this arc in centimetres and the radius also in centimetres, we'd have centimetres divided by centimetres and the centimetres would cancel, which explains why we don't have to write radians here. When you're measuring in radians, it's just a number and it doesn't have any units at all. So look out for questions that are asking you to work with degrees. That is a trick question and you need to alter the question first. So let's rewrite it. What we want to actually differentiate is the cos of. Now how do you change a number from radians to degrees? You multiply by pi over 180. So I'm going to get pi x over 180. And now I can differentiate it. So I've got a little mini function here now, don't I? So when I differentiate the cos of a function, I get negative f dash x. Well, if I differentiate this, I just get pi on 180. And then I need to write the sine of the actual function. So I've got the sine of pi x over 180. What looked like a very innocent and simple question actually had a reasonably complicated answer. Now, if you wanted to differentiate one of the reciprocal functions like sec, cosec, or cot, here's my tip. Rewrite it as sine, cos, or tan of some angle, and then just use the chain rule on it. Don't need to memorize any of these things, but if you get a question like this, just take your time and rewrite it in some steps. So for example here, if we want to differentiate cosec x, rewrite it as 1 over sine x, then rewrite that again as sine x to the power of minus 1. Now how do we differentiate this? Well, we bring the minus 1 down the front, and you can write minus 1 or just write a minus because it's going to be minus 1 multiplied by some stuff. We differentiate what's in the brackets and toss that out the front as well. That'll be cos x. Then we rewrite what's in the brackets and drop the power down by 1. So what we effectively get then when we tidy up, we can write this part as 1 over sine of x squared, or sine squared x, and on the top we've got minus cos x, on the bottom we've got sine squared x.